So yeah, thanks for inviting me for this talk, and I'm really happy to be here. And it's great to see so many people attending. So I'd say I'd start right away with my presentation. So I'll try to see if screen sharing actually works. Ah, no, it doesn't. Should have checked it before. So there's some permission problem as always.
What do I have to do? Hang on a second. So
might be my problem here.
No, the host has to
open system preference. Security settings in Mac OS X. Oh, my goodness. Yeah, that's a new laptop. All right. Now, problem is I have to reopen Zoom. So hope I'll be back.
You drop out for a second.
Sorry about that.
It's all right. I'll sing along while we're waiting for you. It's all right.
Who's that running the UK Smalltalk Zoom account today?
Sorry?
What's your name?
Oh, Tim. Sorry, yeah, it's a good point. It says UK Smalltalk. Yeah, no. Normally Giovanni is behind the name, but it's Tim McKinnon this month. So
Oh, thanks, Tim.
I said I would stand in for him and kick things off while we wait for Michael to just come back.
All right.
There he is.
Yeah. I'm back. That was quick. And now I can see my windows and can try to share them. All right. So I hope you can see my screen.
Yep.
Yeah.
All right. Thank you. So yeah, welcome to my talk. I was playing around a bit like last summer with different operating systems, bare metal stuff. And one thing that came out of it is the topic of today's talk. So a bare metal Smalltalk-80 system for the Raspberry Pi. Well, I thought I'd give you a quick introduction. Here we go. So yeah, I'm Michael, obviously. So I studied computer engineering and applied mathematics in Germany many decades back, got my PhD more than 15 years ago now. And back then I was working on dynamically adaptable operating systems. So how can you change the behavior of an operating system at runtime to implement, for example, updated security policies, optimizations, stuff like that. A bit inspired by Muscle and Synthesis OS. And then I had different academic positions like in Germany, but also in the UK. So I was a senior lecturer at Leeds Beckett University. I worked at Oracle Labs in Cambridge for a year with Tim Harris. In 2016, I went back to Germany to take a position as an associate professor at Coburg University. So, well, at least the people from the UK should probably know Coburg, so the hometown of Prince Albert, the husband of Queen Victoria. And well, since about a year, I'm now in the far north here in Trondheim in Norway as an associate professor for compiler design. But my interests are not only in compilers. So my interests are in the intersection of compilers, operating systems, automatic parallelization of existing code, and also dependability and embedded systems. So why did I think about, working with Smalltalk? I'm not a Smalltalk expert, so most of you know much more about Smalltalk than I do, I'm pretty sure. But nevertheless, I got some inspiration. And the first inspiration was by that very nice person you can see in the picture here. So Niklaus Wirth, you probably all know him. So a retired professor at ETH Zurich in Switzerland. And he's well known for his work on the Pascal, Modular, and Oberon languages. And what I found fascinating about his work is that he always tried to use the research outputs, like a new language, a new system, in teaching at the university. So back in 1985, he invented yet another new programming language, and Oberon was thought to be very minimalistic. So by cutting out all the superfluous stuff from Modular and Pascal, and this was started in 1985 in Switzerland. And he didn't only create a language and a compiler, but also a hardware design for a workstation called the Ceres with a National Semiconductor 32,000 CPU. Probably, if you knew that thing, you probably forgot about this by now. And revolutionary by then, because the Macintosh had just come out, was bitmap graphics and the mouse. And Niklaus was also inspired, of course, by what happened at Xerox PARC in Palo Alto, because he was there on a sabbatical, I think twice for half a year, before he got the inspiration of, I want a machine like the Xerox Alto, but we couldn't afford it. They couldn't afford it back then. So essentially he decided to build his own. And when he was retired, like in 2013, he decided to it's still an interesting system, all this Oberon stuff. So let's try to see if I can get an updated version working. And he revived this Oberon project from 1985. But of course, the CPUs that were used back then, the National Semiconductor 32000 series, was quite outdated. I think it was not even in production anymore. So he set off to build his own hardware design. So he designed his own RISC processor called a RISC-V, not the RISC-V you probably hear about every day nowadays. It's very minimalistic RISC design again on a pretty inexpensive FPGA evaluation board by Xilinx. And the fascinating thing about this is that this system is 100% open source. So you can download the descriptions of the hardware in Verilog. You can download source code for the operating system, compiler, the graphical user interface, and all the applications. And it runs in, well, very little memory, like it needs about 1 megabyte of main memory. It has a graphical user interface. It runs, well, in a useful way in a 25 megahertz system. So that was very inspiring. And I said, yes, I think that's an alternative way to build computers that is, reminds me of my youth in the 1980s when I was a teenager and we played around with Apple IIs and Commodore 64s and all these things, where you could really understand the system and you could dig as deep down as you wanted, and there was still something new to discover, but it was open enough to understand. So, as I said, I wasn't really into Smalltalk for a long time. So the closest encounter I had with Smalltalk was programming in Objective-C on Next machines and later on Macintoshes, OS X Macintoshes, obviously. But I thought playing around with relatively simple operating systems would be great also for my students. And I found out when I came here last year that we had a severe lack of teaching and research topics in whatever was system level software development here at NTNU. So operating systems, compilers, runtimes, JIT compilers, all of this students really wanted to learn more about. So I thought, let's start to see what our students are capable of and announce some master student projects. So here at NTNU, we have a master in what the Norwegians call data technology, so computer engineering. And they have a one-year project starting off with a introductory project and ending with a master thesis. And I wanted my students to learn more about operating systems and also compiler internals. Of course, when you do such a project, you can't really just give a student like a Linux system and say, oh yeah, port it to a different architecture, because the student is going to hate you afterwards, obviously. So I was looking for systems with a complexity that was low enough, with systems that were simple enough for a student to realistically understand and being able to extend and modify in the term of such a project. And one of the ideas was to explore what the challenges are of porting some of these operating systems and compilers to RISC-V. Now, not the Word RISC-V, but the Berkeley RISC-V by Krista Asanovic and colleagues, which obviously is, well, very, where there's lots of talk about on the internet right now. So I started off with some systems I proposed my students to work on. One was actually Project Oberon from ETH, which we have running on RISC-V already now. It's on GitHub. And two of my other students are working on Plan 9 and Inferno, so both from Bell Labs, which are also very interesting operating systems, I think, especially in the context of Internet of Things applications, networked applications, and so on. So I like to discuss stuff like this with a good old friend of mine from the time when we were students, like 20-something years back. So Michael is also online here. So hello, Michael. Michael is, unfortunately, I'd say, working in industry nowadays. But he was a postdoc at the Hasso-Plattner Institute in Potsdam. I think I got this right, from 2006 to 11 in Robert Hirschfeld's software architecture group. And I think I also saw Robert here online. So hi, Robert. And one of the things he was involved with I found very interesting is NX Talk, so a Smalltalk-80 implementation for Lego Mindstorm's NXT, so an ARM7 CPU that actually ran Smalltalk bytecode in order to do typical robotic applications. So I wrote him an email like, oh yeah, these are projects my students are going to work on, like Plan 9, Inferno, and Oberon. And I think I'm paraphrasing this, I'm not his exact words, like, hey, you forgot about Smalltalk. Yeah, he's right. And by coincidence, last year it was the 50th anniversary of Xerox PARC. And so the idea was like, can we get some sort of Smalltalk ported to RISC-V originally? So why did we choose Smalltalk-80? Well, to be honest, I want to start it with a very simple system that has a small size. It's very elegant. Squeak and Faro, for example, are obviously also open source, but I thought starting with Smalltalk-80 gives us an idea of what the complexity of this task is. And of course, there's very good documentation in terms of the Blue Book and also all the other books from the early 1980s that described like ports to different systems at Apple, at HP, at Tektronix, which were very interesting to read about. So, by coincidence, last year, 2 new open source Smalltalk-80 VM implementations were published as open source. So one was by Dan Ingalls, written in C++. This was a Smalltalk-80 VM intended to run the original Smalltalk-80 VM image based on SDL as a graphics and I/O library, plus using simple POSIX I/O, so open read write Unix calls to implement file accesses, file system accesses. So this runs hosted under Unix, Mac, and Windows. Another version was by Rochus Keller. He actually built 2 bytecode interpreters based on the Blue Book description, one written in C++ and the other in Lua, running on LuaJIT. And I think he based this on a previous work of his, which was an Oberon system, so a project Oberon system also based on LuaJIT. So here we have a circle back to Oberon from Smalltalk, which is interesting. What really helped me in understanding what was going on in Smalltalk was a very useful tool that Rochus built, a Qt-based class browser, which also runs under whatever Unix or Windows you can imagine, that was able to just let you browse the original Smalltalk-80 VM image class hierarchy. So that helped a lot in understanding and really getting to know what was going on. So this was a great basis because, to be honest, we didn't want to start writing our own Smalltalk-80 VM, even though this would be a quite interesting experience. But yeah, we wanted to keep it small and simple at the beginning. So one person that was really, really helpful with this is the guy you see here. This is Mario Wolsko. So as you probably know, in the early 80s, Xerox tried to, find some companies interested in commercial Smalltalk-80 ports. And there were teams at Apple, at DEC, at HP, at Tektronix, building various versions of Smalltalk-80. These are described in the Green Book, I think. But there was also some interest in academia. And Mario Wolsko was back then a master's student at the University of Manchester. And in 1984, he started to get interested in Smalltalk. And he wanted to port it to a system that was ubiquitous, I'd say, in the UK, at least in UK universities back then, the PARC workstation. I found out we also have one in our museum here, which is fine. First, he started off without having any Smalltalk image. So he just read the Blue Book, built his own VM, and then wrote some small test bytecode sequences to test his machine, his virtual machine. And later on, near the end of his thesis, he actually obtained an original ST image 9-track tape from Xerox. Mario went on to work at Sun Labs. He's now at Oracle Labs, so he stayed at Oracle after the takeover. And yeah, I met him several years ago. So he's a really great person to talk to, which is nice. And he helped out quite a bit with getting all these Smalltalk-80 efforts going. So this is a citation from his website. So more than 10 years after his master thesis, he was asked by John Maloney of the Squeak group. So they worked together on Self at Sun, whether Mario could give the Squeak group the original Smalltalk-80 sources he had originally typed in from the Blue Book, as apparently the original sources were lost somewhere. This is great because Mario made all this available on his website. So you can just download the original Smalltalk-80 image as it was prepared by Xerox like in the early 1980s. And he got his system to work, which is fascinating because it was a lot of work on the PARC, which had quite some serious hardware descriptions. So if you're interested, his master thesis is really interesting to read from a historical point of view. So you really see what he had to struggle with and all the problems like cross-compiling stuff on a WAX, transferring things over a serial line to the PARC, and then trying to debug all that stuff. So yeah, that reminded me of my first steps in, assembler programming in the 1980s. And yeah, it's a lot of work, but it sounded like a lot of fun. So we have a Smalltalk-80 VM, or actually two implementations of the Smalltalk-80 virtual machine. We have the VM image, thanks to Mario. So I thought, before I just give this to my students, because they were already busy with their other projects, I'd try to get stuff working myself. So Smalltalk on a rainy weekend. Unfortunately, here in Norway, you can also have lots of rainy weekends in summer. And I read one of the articles by Dan Ingalls in this famous Byte magazine from the early 80s. And well, I'm an operating systems researcher. And this, of course, caught my interest. Like operating system, he defined as an operating system to be a collection of things that don't fit into a language. There shouldn't be one. So I spent the last 20 years researching things that shouldn't be there. So, but anyways, I thought, let's try. I mean, if Dan Ingalls thinks this works, and this has worked on several Xerox machines before, obviously, we can maybe get that running on a more modern platform. So I was thinking about which platform that would be useful for a bare metal system could we use today. Now, I said we were targeting RISC-V, but RISC-V back then mostly ran in emulators, so you didn't have real hardware. And I wanted to have, the experience of really getting it to run on a real piece of hardware. And so, well, I taught a course back then in Germany on operating system construction for ARM processors. So I thought, yeah, maybe I could make some use out of this. So not only building embedded systems, but trying to see how much work it would be to get a Smalltalk virtual machine to run on a Raspberry Pi. Because, I was living in Cambridge for a year. So when you live in Cambridge for some time, you end up with a lot of Raspberry Pis somehow. And I had a couple of Raspberry Pi Zeros lying around. So the question was, can we actually run Smalltalk-80 on a 5-pound Raspberry Pi Zero, so the smallest system that's available? Well, comparing the hardware features between the Raspberry Pi Zero from 2016 and the Xerox Star from 1981, it should be possible. Like, I mean, we have 125 times the CPU speed. We have like 1,000 times the RAM. We have like 1,000 times the disk. And the only thing that didn't increase that much was the video resolution. So back then, the Xerox had about 1 megapixel. And now we can have like 2 megapixel. But of course, we're no longer monochrome. We're in 32-bit color. And of course, we reduced the price by a factor of like 4,000, which is great. So yeah, that was the plan for a rainy weekend. But of course, I didn't want to start from scratch. That would have been fun, but that would have been too much work for a weekend. So I thought, what's required to run Smalltalk-80? Not a lot, as it turns out. So essentially, the initial machines running Smalltalk, like the Alto, didn't have that much hardware. So what's important to get a Smalltalk-80 system to work? Of course, you need a frame buffer graphical video output. You need some sort of input like a keyboard and obviously a mouse. A 3-button mouse would be ideal for Smalltalk. And you need some sort of storage medium. So essentially, all of these can be more or less easily attached to Raspberry Pi Zero. So you have an HDMI connector for video. You have an SD card, obviously, connected using an SPI interface that comes with a FAT file system, which is pretty simple. And you have a USB host interface or USB OTG on the Raspberry Pi Zero to connect keyboards and mice. So essentially, what we need to get a VM running is some sort of interfacing, some sort of, well, in operating system terms, it would be device drivers to control your video, to control your disk, to control your input devices. And I started looking around. Is there actually an example code that would help me with this? Because, you know, when you start reading datasheets, and the Raspberry Pi datasheets are still, unfortunately, pretty incomplete, well, you spend much more time than a rainy weekend. So I thought, let's try to see which features does Dan Benai's original Smalltalk-80 system that is hosted on Unix actually need. So as it turned out, the screen and keyboard and mouse interface was all realized using the SDL2 library. And the file system, he was just using standard POSIX calls to Unix or to a POSIX emulating library on Windows. So I took a quick look at GitHub and found something interesting, which was a Raspberry Pi bare metal environment by Marco Maccaferi. And this, by coincidence, included SDL2, an implementation that ran on the Raspberry frame buffer, and which also linked to a bare metal USB driver library called USPi by René Stange, which is written in C. So it was pretty simple to link the C++ code of Dan Benai's implementation to the SDL2 and USPi-based bare metal environment. So we already had something like video output, keyboard, and mouse input. What was missing was simply file system access. And that's a very often used FAT file system library by a person called Chan. You see it everywhere in all embedded operating systems and so on. And this could be easily integrated. Now, the problem here was that this FAT library needed some sort of adaptation because it didn't support POSIX file system calls. So the biggest piece of software as glue code to write was an adapter that just translated typical POSIX file system calls to the FAT file system calls supported by the library written by Chen. So that was actually work for a rainy weekend, and amazingly, I got a prototype running after 2 days. And here's the first video I took of this. It's playing. I hope you can see it. So I'm just starting one of the standard Smalltalk demos here to see how fast can it actually draw on the screen. So how fast is our bitplit implementation? And you can see, well, yes, I think the original Xerox machines weren't that much slower. So this is the overhead probably, which we get by having an SDL layer in between by just setting and deleting every pixel on its own using SDL calls, and then having non-accelerated frame buffer access from SDL. This made the system pretty slow on a Raspberry Pi Zero. And I thought, well, it's probably not ideal. We should try to do something about it. Well, just let it finish here. And then you see the typical Smalltalk-80 effects. So you can draw anywhere on the screen, as you probably know. And then when this drawing program finishes, the window environment isn't automatically restored, but you have to restore it by hand, which was an interesting experience. But of course, it made the system quite a bit simpler. All right, so it was working. It was working amazingly well. It had a number of interesting problems.
Sorry, Michael, I don't think we actually saw the video, but I think it's probably Zoom that doesn't kind of play video
sorry
properly.
about that.
But maybe you can make a link to it available afterwards or something.
Yes,
we can sort of
certainly.
check it out.
All right, I thought that would be working. Thanks. I'll post the link afterwards. All right, so I thought what might be interesting to you is how do you actually bring up such a system? So if you want to get everything running at once, usually you fail spectacularly because, you need to integrate all the stuff and then you need to resolve all the dependencies, and usually you end up, just debugging, and you're frustrated. So I started initially with a system that just used the SDL interface, but didn't use the file system support because I hadn't written the MS-DOS interface or the FAT file system interface functionality so far. How can you do this? I mean, when a VM in Smalltalk-80 starts up, the first thing it does, it reads the VM image from disk. Well, we have half a gigabyte of RAM. So the initial snapshot of this VM easily fits into RAM in addition to all the other stuff we need. So what I did is I just created a very simple big array of 1 million characters and just translated the binary file of the Smalltalk.
Michael, the slides are not changing.
Okay. Well, can you? So there should be a slide called Bring Up now. Can you see it?
We're still seeing the beginning of the slow video from the.
Okay, so I'll probably need to start sharing again. Something strange. All right.
I think Zoom got confused with the video output somehow.
I think so.
Yeah.
Okay, so now there should be a slide with the title of Bring Up.
Hang on, I think it's still loading. It's still blank for me.
Okay.
Yeah, still blank.
I need to figure out what's going on here. Ah, yes, maybe.
Is it swap screens or something? Or?
Yeah, it's right. Next try. Is this any better?
It says started screen sharing, and then press escape or double click to exit full screen mode.
No, that's not enough.
Oh, there we go. That's it. Maybe didn't like full screen mode, I think, maybe.
Okay, can you see a slide titled Bring Up now? Or?
We can, yeah.
Okay, thank you. All right, no idea what's going on here. So yeah, I started off without file system support because getting all of that stuff to run at the same time would have been quite a challenge. So luckily we have enough RAM on the Raspberry Pi to just store a 1 megabyte virtual machine image in addition to all our code. We need to get the virtual machine running and our bare metal library. So I just converted the VM image to a large hex array of 1 million entries and loaded this at boot up into the object memory of the Smalltalk-80 interpreter. So just using a single big array. So that made life quite a bit easier because then you could figure out what's going wrong when startup. And actually, when I did this, amazingly, at the first try, I got a window, I got Windows painted, and it seemed to work quite well until I got the effect you can see in the middle picture here. Like you have a dialog when you try to save a file in the editor in your browser. And well, actually both buttons seem to be pressed and the system appeared to hang. So that was when I found out that we need a bit of additional functionality in Smalltalk-80 because there's a timer that actually enables the buttons to blink when you move the mouse outside of this rectangle of the alert box. And this timer wasn't implemented, so it was just waiting forever. So after I found this out and implemented the timer, actually I got this to work. And drawing was pretty slow at first, but it was surprisingly flexible because, you know, very many systems of the 80s are restricted to a fixed resolution, like the original Macintosh running at 512 by 342 or something. And in Smalltalk, you can actually change the resolution of the display on the fly. And this enabled me, for example, to get it to work with this nice small 5-inch LCD, which has a resolution of 1280 by 720. But we also had some nasty surprises. And one of the nasty surprises is I tried to increase the resolution beyond a megapixel, and the system simply crashed. So we are running out of memory somewhere. So this is a limitation of Smalltalk-80. I'll talk about this in a bit. Okay, so this was 2 days of work, so a nice proof of concept. But we had a number of problems with this. So first, this code I was using for the bare metal library by Marco Maccaferi was like 6 years old at that time. So it didn't contain any support for more recent Raspberry Pi versions. So essentially, it didn't run on any ARM v7 machine, so any machine starting with Raspberry Pi, because it was just having support for the ARM11 core in the Raspberry Pi 1 and 0. And the old US Pi library had a lot of problems with USB hubs in that it didn't detect devices connected to a hub, or only one of two devices at startup, which isn't too problematic if you have an originally Raspberry Pi 1, because this has multiple USB ports, but the Raspberry Pi 0 only has one USB OTG port, so you need a hub to connect keyboard and mouse. So this was my motivation for actually, well, thinking about can we actually have something that's more complete and more up to date, especially since drawing using SDL was also quite slow. And so I started to look around a bit more and found that René Stange, who was also the author of the US Pi library, also built a bare metal environment called Circle. And this actually didn't use SDL. It allows you to directly draw into the frame buffer. It had updated USB support, SD card support, FAT file system. It also has Ethernet and Wi-Fi support, which we don't use at the moment. And so what I had to do is to kick out all the SDL code from the original implementation of Dan Benet's virtual machine, replace it by direct frame buffer accesses, and then I could easily adapt my POSIX to FAT code adapter to access the file system. So most of the work actually was writing lots of glue code. I was standing on the shoulders of, well, giants here, let's say, because, well, most of the work was in the Circle bare metal library, and on the other hand, of course, in the Smalltalk VM implementation. But it was amazing that I could get it to work in a relatively short amount of time. So this took another 2 or 3 days until it started to work. And this now works on many more machines. So it works on machines starting from a Raspberry Pi 1 or 0 up to a Raspberry Pi 4 or 400. And I have several of these machines here. So I'm testing that from time to time, yeah. So what's the status of the project? Well, I uploaded the source code to GitHub. So I called it Crosstalk, well, because I had to cross-compile it and I couldn't think of a better name. It has a number of limitations, obviously. Some are due to the Smalltalk-80 system we're basing it on. So the amount of memory we can use, because it's a 16-bit based VM, is a bit limited. I think we have about 1 megabyte of object memory that we can use. As I already mentioned, the video resolution is limited, so we can have, well, 1 megapixel, or to be exact, 2 to the 10th pixel, and only monochrome. But of course, that's a limitation of the original system, and I think one can live with this. What's currently a problem is that we were using an older version of the Circle library, and this has a bug on ARM11 systems I haven't been able to fix yet. So currently, when you try to use drawing primitives in Smalltalk, it crashes somewhere on the original Raspberry Pi or on the 0. And amazingly, these bugs didn't show up in my original version with the other bare metal libraries. So I need to find some time to debug this. That's not simple to debug. I already spent a couple of days on it without getting any further. So that would need some work. Or maybe I can find a student trying to do it, but I'm not sure if this is great for the student. So one thing I'm going to try is a near-term plan. There's a new Circle library revision release 43.2, which is about half a year more recent. And just to check if simply updating this will already help with some of the problems here. So that was a fun little project intended for a weekend. Well, it took a couple of more weekends over the summer, but well, we're in Corona times, so you have more times left over. So what was the impact of the project? Well, 15 minutes of fame, well, internet fame in this course. I actually sent Michael a very first image of the Smalltalk system, and he tried this on one of his Raspberry Pi Zeros, and he published a tweet on Twitter with a video, so wait for it. Yes, this is a Raspberry Pi Zero booting directly into the Smalltalk-80 implementation by Dan Ingalls. This got quite a lot of feedback, so people really liked it and obviously retweeted it and so on. And somehow it ended up on Hacker News, and we were on the second place on the front page for a day. I would have never guessed this. And from there, it spread to sites like Hackaday, Hackster.io, and so on and so forth. Got lots of feedback. Lots of people actually liked it. Like we got like 200 something stars on GitHub. What I was wondering is I didn't really get much feedback. So I was wondering, did actually anybody try it out and use it? Not so sure, but at least I was really happy about that people liked it. And well, it taught me that alternative systems, not only Smalltalk, but also, you know, Plan 9, Inferno, Oberon are very popular still, especially with people in the Hacker News community. So everything you post in Hacker News concerning one of these systems, which is somehow new or interesting, well, rises up quickly to the front page. And our Oberon RISC-V system by my student Rikke was published like 2 weeks ago, and it also was on the front page on a very high place for a couple of minutes. Well, well, I can't buy myself anything for this, but I think it's nice to get some recognition. And that's all, virtual internet points, right? So I'm not really happy with the state of the system. So to repeat, Dan Ingalls, an operating system is a collection of things that don't fit into a language. There shouldn't be one. And then I took a closer look at the Circle library. And I was wondering, isn't this actually an operating system just hiding as a bare metal library? It has 214,000 lines of C++ code, including some optional libraries. To compare, the Smalltalk-80 VM implementation by Dan Ingalls has about 13,000 lines of code. So maybe we should try to build an alternative approach using a very slim runtime that's just tailored to the requirements of a Smalltalk-80 system. And I'm not the first one to think about this. There was a paper published like 4 years ago by Jan Wietek and colleagues about a very, very simple runtime for a Smalltalk system called Nopsys. This ran on x86, and this was about 4,500 lines of code. So 2 orders of magnitude smaller than Circle. So one of the ideas, and that might be an upcoming student project, is to actually get Nopsys to run on the Raspberry Pi to support Smalltalk, and then not only a Smalltalk-80 system, because the Cognos system would also, for example, support a Squeak VM. The other thing I was thinking about is Smalltalk is great because I can look at so many things, I can change things on the fly, but when it comes to hardware, well, it's all closed, especially on the Raspberry Pi, which is not as open as I would like, unfortunately. And this reactive principle, every component accessible to the user should be able to present itself in a meaningful way for observation and manipulation, this stops somewhere. And I don't like this. So I was wondering if we could be more open, similar to Project Oberon, where we not only have the operating system and compiler and applications as open source we can modify, but we could also modify the hardware. So of course, this can be made reality now because we have open source hardware like so many RISC-V CPU implementations. And we also have an open source synthesis toolchain to create FPGA images, so FPGA bit files from Verilog source code. So there's Yosys, SymbiFlow, and there's also high-level toolkits using, for example, Scala-derived languages that enable you to easily build a system on chip. And that's a system we're trying to build here now. So build an FPGA-based Smalltalk-80 RISC-V system, inspired again by Niklaus Wirth's ideas, but of course a system that could also work with Oberon, and maybe also with Plan 9, Inferno, or even a standalone Lisp system. So for Plan 9, we would need an MMU. That would make the system more complex. The other systems could get away without having an MMU, which would keep the system very nice and simple. So my vision behind this is, can we actually build a completely understandable open source computer where our students can learn from, which everyone can take and modify, where you can actually remove all the things that annoy you and add stuff on your own, like the systems I was used in the 1980s, but now with graphical user interfaces and network and all the things you want to have. And of course, there's some projects that are already trying to do this. You have probably heard about the Purism Librem 5 smartphone and all the nice products by Pine64, like the Pine Phone or the Pine Book. There's an interesting project by a person in Berlin, Lukas Hartmann, and he started crowdfunding a project called the MNT Reform. It's an open source laptop with a quad-core ARM, a Freescale IMX8 core running Linux. And this system is as open as it can be. It's open source PCB, it's open source software, it's open source documentation. But all of these systems lack open source hardware. So here, RISC-V may be an interesting approach to try to build an even more open system. What might be interesting to some of you, Lucas also built a bare metal operating system for a Raspberry Pi. He built a Lisp-based system called Interim Lisp OS. And this unfortunately only runs on a Raspberry Pi 2 right now, because this was probably a rainy weekend project for him a couple of years back. It's really interesting to look at, and you can get some inspiration from that. And if you go further, there's very interesting ideas by a colleague at the University of Kent, Stephen Kell. He has some really interesting ideas of how to connect the openness and introspection and understandability of Smalltalk and connect this to common Unix systems nowadays. So I'm coming from a Unix background. Originally started with a Sun 3 machine on Sun OS, and I'm still more or less a Unix hacker, but I try to keep an open mind. And I think having the best of both worlds might be really, really interesting to have. So I would like to close with another bit of history. So we have a computer museum at NTNU. And we have, as I found out when digging through our collection, which is not really cataloged, we have very many interesting machines. So we have several Xerox Star machines. We have Tektronix 4406 and 4404 Smalltalk machines. We have some TI Explorer Lisp machines. We have an Appleizer, which was a machine that Apple originally developed their Smalltalk-80 system on, and many other systems like PDP-11s, Vexen, and exotic Norwegian machines I've never seen before. So one thing we're trying to do is to get our students to really get a feeling of how these machines worked in the 1980s. So we'll try to restore these systems to working conditions using, well, student projects working together with students. And when this Corona situation might finally be over, I would love to have a living exhibition of all these 1980 machines, maybe with the context of this is the beginning of all the artificial intelligence you're now talking about. This was developed on Lisp machines, on Smalltalk machines, and so on. And I think some of the students seem to be really interested in this. Now we have a practical problem that we just don't have access to it due to Corona regulations. Something else that might be interesting for you is that Sesma Robito has started work on a Tektronix 4404 emulator. It's not very far. I checked his blog. He started last year. He says it's like 20% complete, but I would find it interesting. So the Tech machines were Motorola 68K based and ran, well, a Unix-like operating system, but then had a very optimized Smalltalk machine, which is exactly what is described in one of the chapters of the Green Book. So I think that was an interesting platform. And I have one of these machines on the desk here trying to make an image of the disk first, but this has some practical problems, like how can I read an MFM disk from a modern computer? Anyways, I hope you found my talk a bit interesting. I didn't go into too much details of the nasty C++ stuff I had to do, because to be honest, I think that can be quite boring, and it was a bit frustrating until, well, it really started working. So I'd like to close my talk with this slide and have another set of references for you in case you want to dig deeper. So thanks for listening, and I'm happy to answer your questions.
Thank you, Michael. That was awesome.
Thanks.
Yeah, clap from everyone.
Great talk.
Funny what a rainy weekend can do. Which I could start my video actually. So yeah, we'll open the floor to questions. I think you can just shout them out, but you know, if you want to put something in the chat, I can read them out.
There's lots of stuff in the chat I see now. I will just start. Okay. People remembering the National Semiconductor and the PARC. Yes, that's great. So I was born in 1970, so I was happy to be able to afford an Atari ST when it came out in Germany, like in 1986, and it was so much better than the Apple II. But still, I like the Apple II. So yeah, and it's actually fascinating because these machines were so simple, at least when you look at them today. Okay, people who didn't see the video, we'll post the link later. So that's a zoom effect. That's interesting. Another idea is a shimOS. Open Smalltalk OS up on Alpine Linux using a frame buffer. And this is using Muzzle as the libc. Okay, that's interesting. I need to look at that. I haven't checked that one out. And there was Squeaknos. Yes, there were also some interesting Squeak developments for multiprocessor systems, which I think would also be interesting on the larger Raspberry Pis, because currently we're just using one of the cores, which is a bit of a shame. What else do we have? So many people liking it. That's great. Yes, really interesting idea to get students to own their own software environment. Yes. That's exactly what I want to do. So in Germany, I taught a course on operating systems development for ARM Cortex microcontrollers, so embedded operating systems essentially. And students really liked it. So I had like 50 students in that course each year. And they were working in groups of 2 or 3 students, and each of them actually managed to build their own small preemptive multitasking kernel, including all the nasty bits like changing the stack around and getting that to work, and getting interrupt handling to work, and getting system calls to work on ARM. So that was great. And some of the students went on to do their masters in industry. And they gave me feedback of like, yeah, we're building this embedded system for our industry customer now, and I'm actually basing the software on the operating system we wrote in your course. Yes, that's exactly what I want to hear as a teacher. Like students really not only learning stuff and forgetting about it, and it was a nice experience, but really taking that stuff along and using it. So I was really proud, I must say. Yeah, what else have we got? Does a Circle allow this to run on the IMX M8 and on the Reform? No, Circle is at the moment just simply supporting Raspberry Pis. I have a number of Pine64 boards here, which use Allwinner and Rockchip ARM multi-core systems. My interest would actually be importing some of the systems to this Pine64 hardware, which is really nice. And the Pine64 guys are really supportive. So they have this really great Pinebook Pro. I ordered one. I have it here. So it's an absolutely fascinating machine for $200. So it has like 6 ARM cores, a big little architecture of 2 big and 4 small cores, 4 gigs of RAM. It can even have a PCIe SSD. And I would think that would be a really great laptop platform for building a standalone Smalltalk system. But porting Circle would take a lot of time. So my idea would be to have something that's leaner as a runtime and then try to port this. Because yeah, you spend most of the time just doing device drivers, and that's not really exciting work. And I don't want to torture my students to do device driver development.
One of the things that, I mean, something that drove me to think about the idea of a shimOS is that the USB, just the USB, which is a kitchen sink, spec, is just huge. And
Yes.
I don't want to be spending my time doing device drivers. I mean, it's just, an area that the amount of information that you're going to learn for the time you spend there it just seems really small. And so that's why I went the strategy of saying, okay, well, if I use a minimal OS, minimal Linux OS, that it does the bootstrap, it does the USB drivers, you got Ethernet, yada, yada. And then the value added is the Smalltalk VM.
Yes.
So I think about where I'm adding my value, that's in Smalltalk. And so
yes.
For me, that and of course I'm typically myself, I'm using Queese because it's on the order of, 500 to 600 classes, as opposed to like Faro, where you pick up you say Smalltalk, all classes size, and it's like 9,000 and some.
Yes.
It's just that's too big for my head. I've got a smaller head. I've got to understand things. So that's the direction I've been sort of going to. But the device driver thing, requiring device drivers, you really need maybe RISC-V is the way to go. You really need a simple set of devices, rather than if you just take a look at like the startup code for an ARM chip and setting up the VM. And I ported on the 68010 PSOS real-time kernel and did some work in that using a logic analyzer and a prom burner back.
Oh yeah.
But I look at the startup code on like a current ARM chip. I mean, it's just a huge amount. I mean, you take a look at Circle. For the bare minimum, you're doing a huge amount of work.
Yeah.
And it would be nice to have something that's more comprehensible, because the same thing, for hardware, if you like in software, is you say, how do we make hardware be comprehensible and able to present itself and do virtual CPUs and stuff that then map into software conveniently and easily? And that, I think, is a really a current challenge, because the hardware folks, it's just the complexity, the gratuitous complexity, just seems really amazing for the amount of value that they're putting out.
Yeah, so I'm experimenting. We have a microchip PolarFire RISC-V board here, so an FPGA with 5 hardware RISC-V cores on the chip, and this needs about 1,000 lines of startup code before it just really executes the first useful instruction for just tuning DRAMs, for getting all the buses in order, and then you have to boot the multi-cores in a specific order, because only one of the cores can execute code without an enabled MMU and stuff like that. Well, what would be interesting is to take a lesson from all this unikernel development. So you talked about using a minimal Linux kernel. There's an interesting approach for NetBSD, which is called a rump kernel, which was a PhD project by a student in Finland, I think, a couple of years ago, which enables you to actually transform NetBSD to a library operating system that can then be linked to, well, your Smalltalk runtime, obviously. And this doesn't really support the Raspberry Pi at the moment. I gave this a try and I failed, but maybe that would be an interesting approach. An alternative I could think of to make porting VMs easier, there is a well-defined virtual machine interface. So even Apple supports this on the new M1 Macs for ARM, which is Word.io. So Word.io supports virtual frame buffers, virtual input devices, virtual disk and network devices. And this is relatively simple to get going. So another thing that could be provided in the hardware of a Raspberry Pi or a RISC-V machine would just be a hypervisor that provides exactly this Word.io interface. So the VM could be based on that. And additionally, you could run several VMs in parallel or whatever you can imagine, because you have a hypervisor now.
What about starting with a bootloader?
Abstracted hardware does look like an interesting approach.
Yeah, so the real big question is what is the performance impact of abstracting the hardware? And that's actually a research topic I'm thinking about putting more work into. So where do we put the abstractions? Where do we put the complexity? We cannot get away without having the complexity, but we can hide it somewhere. And maybe we should rethink about where we are hiding our complexity in system software design.
Michael, what about starting with a bootloader instead? So the bootloader's done all the hardware normalization.
Yes, that might work, but of course the bootloader will quickly turn into a hypervisor, I think. So maybe not.
It at least gets you out of some of the hardware boot up process, which is really just embedded work, not OS work.
Yes, but of course it increases the complexity. So you can do this on RISC-V, for example. So you have the OpenSBI firmware, which actually boots the U-boot bootloader, and this initializes, well, almost all of the hardware you need. Now the problem is then that costs you like 100,000 lines of C code already. And I'm coming from an embedded background. I like my systems to be small and compact. So I Probably it's a bit too idealistic for modern times, but still, yeah, that really well hinders you in understanding the complete system, because there's some magic happening behind the scenes, because your bootloader is doing all that stuff. So you're not really in complete control of the machine. And as we've seen with all the security problems, Intel and AMD CPUs, all the management mode stuff, running a complete Minix system on x86 CPUs to do system management, I want to be in control of my computer. And that's currently, I don't have the impression that with all the computers I'm using right now, that I'm really in control of what's going on.
You're making me laugh. I do a bunch of stuff with Sarcos Robotics, and we build our own boards. And the amount of code we have to go through to get to the point you're talking about is enormous, and the security issues are all over the place with every new chip design. So
Yeah.
that's a hard problem space.
Yes, definitely. And also for really, really small embedded systems, like we have Nordic Semiconductor here in Trondheim, and they have really nice chips, and they're giving them away in large quantities to our students. And then when you start downloading the BSP for these chips, you have to download 0.5 gigabyte of zip file. And it's absolutely impossible to write any code for these Nordic chips, or at least really, really hard, without using their BSP. And then there's so much stuff going on in the background again. And that's a shame, because there's like more interesting projects I didn't talk about. So one thing I was thinking about, I briefly mentioned this NX Talk system running on the ARM7 in the Mindstorms Lego robot by Michael Haupt and his students. And there's hardware out there with very similar capabilities in terms of RAM and CPU speed, which is in smartwatches right now. So the Pine64 guys have actually built a smartwatch which you can buy for like $25. It's a Pine watch, and this has one of the Nordic Semiconductor chips in it. And it would be great to see, can we actually get a very, very small Smalltalk system to run on this, and maybe even play around with networking it, so we can not only synchronize like contact data or phone numbers or whatever you can imagine, using some strange internet protocols, but maybe using Smalltalk objects we send over a wireless connection. So yeah, that's in the back of my head, but that's a much more elaborate project than I thought. I got one of the watches, but then I was really put off by the complexity of this SDK, unfortunately. All right, shall we go on with the questions? What else do we have?
There's a few more that have popped up.
Yes, great. So David worked at Atari. Okay, he really learned about OS work. So PARC machines in the mid to late 70s. Yeah. The Atari stuff was great. So back then, we got the whole SDK from Atari Germany. They were really supportive. We got all the documentation on the operating system and stuff like that. And I remember the first thing I wrote on the Atari ST was a 6502 emulator, because I was used to writing 6502 assembler code. And I actually have managed to execute the Apple II monitor on the Atari ST. It was just so slow, because emulating a 1 megahertz machine on an 8 megahertz machine without writing a JIT takes some time.
This is David. The original, the Ataris I was talking about were the Ataris from the 70s.
Yes, the 400,
original
800s, yes.
Yeah, the 400s and the 800s. And I have both. And Atari would give you nobody else I could find, they gave you all the hardware specs. So you got all these fantastic sheets with every bit of the hardware. And they gave you all the listings to every piece of software on it. I actually learned all my hardware design originally from playing with those things. That allowed me to build the NBSNet packet switch network boards, my first language. And I was at the same time I was working on PARC at National Bureau of Standards, which is today NIST. But PARC mini computers, that was a fascinating time.
Definitely.
Those things cost $1 million, but
Yeah, and I also learned a lot about computer hardware from Atari stuff. So back when I was still in high school, transputers were all the rage, obviously, like in the late 1980s. And we had a company close back to where I grew up in Germany that actually built electronic music instruments. Maybe you heard about that company called Versi or Versi in German. And we found out that they actually implemented their high-end electronic organs using a network of transputers, and they wrote their own distributed real-time operating system for playing music on a 100,000 German marks instrument. And the good thing back then was the daughter of the boss of that company was in my class at school. So we got a transputer chip for free, a T800, which cost like 800 marks. And we built our own transputer, just learning from whatever was we could get information about the Atari transputer. And also there was this German computer magazine called CT, where they actually published circuit diagrams and software for their own transputer system. So that's how I learned about hardware and software design. It was fascinating times, especially when you were like we were 17, 18 years old back in high school.
That's fantastic to have access. I was working on transputers at the University of Maryland for NSF, and we had a lot of samples because we were doing stuff with TI, and all the work was being done in Lisp. That was actually what exposed me to Lisp.
Yeah, that was great. And yeah, like when I met David May in Bristol several years later, actually he told me, yes, he actually heard about our project. Like there were some crazy high school students building their own transputer back in Germany. I have no idea why or how he could hear about this, but yeah, so it's a small world. And we got it to work actually. That was amazing. Yeah, transputers were so easy to interface because they had all the DRAM controller hardware on chip. But then they were horrible to program in assembler.
That was a fascinating time because right about the time I got exposed to transputers was the first time I saw Smalltalk. I didn't see Smalltalk until 1986.
All right. Yeah. So what else have we got? Oberon was a reaction to the size of Cedar. Yeah, I think so, because that was one of the systems that Nicholas probably worked on, or at least worked with when he was at one of his sabbaticals at Xerox PARC. So yeah. And you know, Wirt, there's this paper by him, A Plea for Lean Software, and he wants to keep software small and easy to understand. And I really like this approach. Sometimes maybe he takes it a bit too far, especially we've seen some of the optimizations he did in the Oberon compiler backend, which we had to undo to get it to work with RISC-V. But yes, it was fun to learn about this.
Can I suggest people shout out your questions to Michael? Makes it a bit easier for him instead of just poring over the the transcript there. I think Bruce, you had something about headless. I saw in there. Have we still got Bruce?
Yeah, you're making me turn my damn microphone thingy on. So I was just wondering if it would be a simplification to have a completely headless image that just in quotes implemented sockets, so you could reach into whichever machine you were trying to build a Smalltalk image on and not have to worry about, you know, USB or display or anything like that.
That would be great, because that is a direct link to the other projects like Plan 9 and Inferno, which actually do this. Because, you know, in Plan 9 and Inferno, everything's a file. So essentially, if you have a file, you can run the protocol over whatever link you have, a serial line, Ethernet, and so on. So it doesn't really matter where your devices are located. So you can have a real distributed system. And this works pretty well, actually. So there's this common, very simple 9P protocol that's actually also used, for example, by VMware and VirtualBox to enable access to your host file system from the virtual machine. And maybe integrating something like 9P into a Smalltalk system, but then, of course, maybe even communicating over objects instead of sockets. That might be interesting. Or maybe getting Smalltalk to talk to a Plan 9 system to do, well, graphical I/O, input, disk access, and so on. Best of both worlds again, I guess.
I've thought of this because many years ago, I attended a Smalltalk Solutions, I think it was, and there was a loudspeaker company there. If I recall correctly, they were running a Smalltalk VM inside of a loudspeaker.
Wow.
Because they wanted to control the dynamics of the loudspeaker. There was no keyboard, of course, nothing. They just had a socket going in and they were talking to the VM.
Yeah.
It wasn't Lin, was it?
I don't remember. It's just a vague recollection.
Yeah.
Yeah, sounds
I think I did
interesting.
some work on research on their Lin recursive stuff, and I think they, to a point, they use Smalltalk in some of their in some. I think of some of their GUIs of stuff. I'm not sure though. Sorry, go on.
Yeah, it would be really interesting for embedded stuff to use Smalltalk there. I mean, biggest problem is probably getting real-time stuff to work with garbage collection, but I mean, that's an interesting problem on the research side, at least, yeah.
Lin definitely were involved with Smalltalk stuff. I worked with a couple of people that were involved in it. One of the problems with their recursive CPU thing was that the British Navy got their hands on nearly the entire output of their hardware, and it mostly got blown up in experimental torpedoes.
Oh, that's a shame.
But
well,
Craig
it's an embedded application where you don't have to be, to be concerned about crash safety, yeah.
Yeah. So Craig and I worked at Interval Research, and we were doing a network system for controlling what we'd call Internet of Things stuff these days. And that was Smalltalk on our own custom strong ARM-based hardware. No operating system at all beyond the sort of basic boot and check that the memory was talking to the right things. Smalltalk, the screen display was just a chunk of memory, and the only thing you had to do was set a value somewhere in a magic address to say, oh yeah, this memory address from here to here is what you try and display. And so there was none of this double buffering for the display that or even triple buffering that we end up with through modern windowing systems. And that could handle interrupts coming in on what we call the media wire, wasn't it, Craig?
Yeah.
At like CD sample rate, so 44 kilohertz interrupt handling in Smalltalk, and it scheduled any other hardware interrupts and stuff as well in Smalltalk.
That's quite an achievement, yes. Getting this interrupt rate to work in C is already difficult, yeah.
Yeah, and that was a 200 megahertz strong arm of the era.
It's a nice machine. So yeah, I was also teaching digital signal processing in Germany, and we used like a 200 megahertz Cortex M4, which should be about as fast. And the students were really struggling to get their filters and Fourier transforms to work in real time. Yeah.
Michael, I had a question for you. Just going on about the socket thing. You have a good sense for how many lines of code are necessary to do some basic sort of stuff. So if you had to build out enough code to talk to a NIC from within a piece of hardware, what scale of problem would that be?
I think this mainly depends on the complexity of your NICs. So there's really horrible NICs out there, like if you read the FreeBSD driver source code for the Realtek 8139, that's a 100 megabit card. I think they complain about this is the most horrible piece of hardware ever made, and it's in the source code for like 20 years. So there are intelligent, well, more or less intelligent cards, which of course there's TCP/IP offload with some chips like the microchip EN28 series, which implement the TCP/IP stack actually on a microcontroller on the Ethernet chip, which makes it really easy. So these things are commonly used with Arduinos or something, because you don't have the code space and the compute capabilities to run TCP/IP on an AVR processor. But these are very limited. So a real NIC, simple ones can get away with just implementing 2 ring buffers and setting them up correctly. But the last Ethernet driver I wrote is so many years ago. I think many things have changed, because you can now have priorities and independent queues. But just a NIC, just getting some packets from the wire and sending them out again, should be made to work in like, let's say 500 lines of whatever code. The more complex problem would be getting TCP to work, but there's interesting low-level implementations. So there's this Swedish guy called Adam Dunkels, who did his master thesis, or was it a PhD thesis, on writing very tiny TCP/IP implementations for embedded systems. So they're called UIP and LWIP for lightweight IP. And he even got the Eurosys dissertation award for this. And he also authored a very small embedded operating system called Contiki. And maybe some of this can actually be reused to implement TCP/IP, because Ethernet alone, I mean, it would be interesting. That was one thing I was wondering when I was looking at the Smalltalk sources. Like, I thought all these Xerox machines were connected using like 3 or 10 megabit Ethernet and ChaosNet protocol. And I couldn't find anything about ChaosNet in the Smalltalk code I had a look at. So maybe getting ChaosNet to work, because that's a bit simpler than TCP/IP, would be interesting if there's a Smalltalk-based implementation of this somewhere out there.
I guess nobody knows that one.
No, that's 25 something years ago. But yeah.
ChaosNet is MIT, not Xerox, I think.
Yeah, but I think they had something going, but maybe I mixed it up. Yeah.
Yeah,
I'll have to check it out. Yes.
Yeah, the Xerox things was called PUP, P-U-P or something like that.
Oh yeah, maybe I was. Yeah, that can be. Okay, so maybe I was. Yeah. I got something mixed up there.
I remember the case that Bruce was mentioning about this company controlling audio system. Lars Bach was involved in there, and the Smalltalk system was called Resilient.
Okay. Never heard of this, I must admit.
Yeah, Resilient was previously called OOVM, so it's easier to search for OOVM.
I found a paper by Jakob Andersen, Lars Bach, Steffen Graurup, and Kasper Lund. Okay, Danes, all right, and some more. Yeah, okay, interesting. More to read. Yes, great, thank you.
That's a different Smalltalk. They have some limitations. They have the blocks couldn't be full blocks. They didn't have closures.
It's a shame. Yeah, that's one of the nice features.
So how far off are we from getting something that, even a headless sort of Smalltalk that we could, run household stuff on, start, hacking the house kind of thing? Or, just if you wanted like to take a Pi 0, you got something working, but I guess it's not networked in any way, hence Bruce's question.
Yeah, so I think what we need is, well, network, obviously, to some sort of Wi-Fi or whatever, or Bluetooth connection, and of course device drivers for the common interfaces to control stuff like SPI, I2C, GPIO pins, to really build a Smalltalk LED light bulb. I mean, if you look at stuff like I think it's a $10 IKEA light bulb, and if you open it up, you find that there's a Cortex M4 running at 100 something megahertz with 256K of flash and 64K of RAM inside, and a wireless chip. So that might be an interesting platform for a very much scaled down IoT. Yeah, Smalltalk on a light bulb sounds good, right?
It does, yeah.
In fact, that would be an interesting project, because there's this NX Talk system by Michael Haupt worked on such a processor, like in the Lego Mindstorms. So it should be possible.
Yeah, in this respect, I wanted to ask you something. For electronics application, I also wrote it in the chat, but it would be interesting to know if the system can be made to go real time or something similar, near to real time, even if slow. But important is that it answers question in a fixed amount of time. This would be great.
Yeah, so for this, we'd probably need an expert in garbage collection, which I'm not. But I found this topic very interesting. I think there's still active research in building very fast garbage collectors, or people really getting away from garbage collection and just using reference counting, which is slower overall, but of course more predictable. I think that's what Apple has changed in Objective-C. So they went from garbage collecting back to reference counting. And what makes the Apple M1 chip so fast is that they actually managed to improve the performance of reference counting by a factor of 6 compared to the Intel CPUs they had before. And that's what's still used in Objective-C and Swift nowadays. So Yeah, interesting research topic, definitely.
Yeah, reference counting still needs a hybrid scanner to get rid of cycles.
Yeah, you probably need to figure out circular dependencies, which reference counting doesn't get, I suppose.
My current engines do a hybrid.
But it could be, I'm guessing, but it could be usually in electronics where the logic is very simple now. Check, if, true, do that, just easy stuff. So can we maybe pre-allocate some amount of memory and don't garbage collect at all? Just say, you can use that memory, it's pre-allocated, just overwrite it.
Yeah, something like having a lock for the virtual machine to disable garbage collection for some time, like you would disable interrupts when you do real-time critical polling stuff. Yeah, why not?
Yeah, I saw only one article a couple of years ago about making Smalltalk real time, and they failed after 1 year or so, and the project ended. I don't remember now who was the people, but still, that would be great because
Yeah, yes, definitely. I mean, the interesting thing is that would enable many more people to just get involved with IoT applications, write their own stuff instead of just buying stuff that's relying on some cloud server out there. And when that server is switched off, well, you're out of luck and you can throw away your hardware. I hate things like these, to be honest, like being dependent on some company on the net that can decide to disable your hardware at any possible moment.
Yeah, absolutely.
The interval research project that Craig and I and a bunch of other people worked on was aimed at what we called fairly hard real time, because we had to be able to respond to the proprietary network stuff at the 4400 kilohertz thing. No, not 4400 kilohertz. That would be ridiculous. You know what I mean?
Yeah.
4400 would be, yeah, that would be impressive. And that we had back then it was the very early Squeak, so it was a very simple mark space garbage collector, no incremental or anything, and it managed pretty damn well most of the time. We had a never quite finished project that Paul McCullough was mostly responsible for, to do a doubly linked list, black, white, red, I think the algorithm was called. It was yeah.
He started off with Baker's treadmill collector, and he was elaborating it.
Yes, and there was a variant by somebody whose name I should be able to remember but can't, that used a 3-phase thing to do it. But that was showing promise. It was definitely going to be slower, but it was going to be reliably no long interruptions.
Yeah, and that's what counts in real-time systems. Yeah, you need to be deterministic, and that's all. That's
really our hard limit was what we could do in the vertical blanking interval of video.
Yeah.
Yes.
I just point out that in the 80s, the guys from the University of Carleton were specialized in real-time Smalltalk, and they worked with the Tektronix guys to put it in their oscilloscopes. So you had the oscilloscopes from Tektronix with Smalltalk, and it really had to be real-time. Yeah,
definitely. And I think there's a web page on the Tektronix Smalltalk scopes out there. Let me see if I can find this. Yes, there it is on c2.com. I think they mentioned some of that stuff here.
Ref count works best if you're trying to do real time or you've got slow processors and the other. And I generally built hybrid collectors because of that, but also it's very important for interfacing to a lot of systems that are ref count only. So when you want to do language interfacing, you have to have a hybrid collector that does both. And the nice part of having a hybrid collector is you can just shut off everything but the ref count part.
Yeah.
And it works fine if you're willing to, get some real-time compromise.
Yeah. So
I'm just gonna kick in now, guys. I'm gonna stop the recording, not end the meeting, but I just stop the recording so that we can kind of get it churning away. Please keep asking questions, but once again, thank you, Michael, for doing this, and thank you for everyone for all these great questions. And I guess I'll point out, I guess the next Smalltalk meetup is the Californian guys. I don't know when that's happening. Craig, it's soonish, isn't it? Is that?
Yeah, that happens. Yeah, that happens in between these meetings on second Wednesdays. And the details are all on meetup.com. Just look for California Smalltalkers.
So, everyone's welcome if the time zone suits, but I noticed you guys quickly turned around the recording so you can kind of watch it the day after. Let's keep chatting here, but I'll just stop the recording now. So I'm just gonna stop that.